we're going to spend a little bit more time talking about polar coordinates before we start talking about vectors, except we're going to move over to the complex plane now. We won't talk so much about that second theorem because we have a calculator that does it in about half a second, and so we'll save ourselves some paper and use the calculator instead for the second theorem. But converting from a polar plane to a complex plane, or the other way around, we're going to actually have to do by hand. So let's say I have a point on the complex plane, and we tend to use z when we're talking about complex numbers, where I have a radical 3 minus I. So one thing that you're going to want to remember is that the constant, or the real part here, we usually say a minus or a plus bi. The a is going to kind of be our x, well, will be our x, and the b is going to be our y. And so if I was going to look at what this looks like in the complex plane, it would look like I'm graphing a radical 3 negative 1, but it's not going to be on the y-axis anymore. We're actually going to change that to the I-axis. And when you label the point, you label that with it that whole expression. So now what we want to do is we want to talk about getting to that point on the complex plane the same way that we talked about it in the Cartesian when we were converting over to polar. So if I was going to open it up an angle and lasso out, what kind of angle would I have to open up to, and how long would my rope be? But it's going to be a little bit messier since it's not an XY plane, it's that Z plane. So if I have the negative radical 3 plus I, and I want to go over to polar form. First, of course, if you're going over to polar, you want to find out what your radius is. So we're still going to need to find r. So square your x part of your coordinate, which is the real part. The y part of the coordinate is the coefficient in front of I, and we'll get a 2. So at least that's nice. We know that this one is a negative radical 3, 1, so we're over in the second quadrant. So that's going to help us find theta a little bit. Sine is y over r, or of course, r sine theta is y and r cos is x. And so now that you have x's and y's and r's, it's pretty easy to figure out where you are. You could have used, since we're in the second quadrant, inverse cos, but this guy is on the unit circle, right? So if I have a negative radical 3 over 2 and a 1/2, I know that I'm at 5 pi over 6. The expression that you're going to use to convert it over is r, open parentheses, cos theta plus I sine theta. Then all you have to do is write it in there. So it's going to look actually messier when you convert it over to polar this way, but it's still going to be a little bit easier to work with than some of these other expressions. Going from the polar form over to the rectangular is actually a lot easier, because all you need to do is look up the cosine and the sine, either using your calculator or your unit circle. We know that the cosine of a 60 is a 1/2, and we know that the sine of a 60 is a negative radical 3 over 2, and so I just take the cosine and sine out. I put those values in, distribute the coefficient of the 4 for the radius, and there we go. I have a 2 minus 2 radical 3I, and many times I'll kind of stick the I in here because it kind of looks like it's snuck underneath the radical, and it didn't. It actually ends right there. If you want to multiply 2 of these or divide 2 of them, there are these very nice formulas, although they probably don't look very nice on the page. If you have 2 points that you want to multiply, you will multiply the magnitudes, we'll come to call them, right? So the radius out front, and then you will add the angles. If you're dividing, you will divide the magnitudes, those coefficients, the radii out front, and then subtract. Watch out for those negative angles. A cos of a negative 30 is the same as a cos of a 330, right? Because we don't want the negatives in here. And same thing in here. This theorem works through a very long formula to get you to swap over 1 plus I to the 5th power. All of this is not necessary because a calculator will do it all for you. And so in case you forgot where your I is on your calculator, I will pull up the calculator, go into mode, 1 plus, and the I is at second decimal point, and then raise it to the 5th. Done. If you get crazy numbers in here, you can hit Math, enter. We'll change it to fractions if they can be changed to fractions. If they're irrational, then you'll just get the little dots. So no need to go through the long process of finding out what that would be by hand when we can type it in the calculator 2 seconds later. Unfortunately, you cannot do that when you're looking for roots, and we will have to use this lovely formula. This is the easiest way I can explain this formula. You're going to start with an angle, and when we talk about roots of complex roots, I think of it as you're slicing up the unit circle into that many slices of pizza. And what you're going to do is, from your starter, you're going to say, all right, if I want to break up this part into 3 roots, 5 roots, 6 roots, what would the angle of the pizza slice have to be in the middle? So if I had a pizza with 5 slices, actually I'm going to do 6 slices because it's quick to divide, and all the pieces were the exact same size in here, 1, 2, 3, 4, 5, 6. Then I know I have 360 degrees. I have 6 pieces of pizza. Each angle measurement in here has to be 60. That's what we're looking at in here. This part will tell you how long the pizza is. So is it a small pie or is it a big pie? Z sub k, where k is the root that you're taking, right? Well, actually, the root that you have taken, I guess I should say, because we'll have multiple roots. It's not like you take a square root of 4 and it's just a 2 or a positive 2. We're going to get a lot of roots. N is the root that you're taking. R is the radius that you're going to need to find. Theta is going to be the theta that you start out with. Of course, a lot of times they give it to you in Cartesian and you've got to go over to polar, so you got to find that initial theta. Again, N is the root that you're taking. The 2k pi is going to help us tick around the circle, and then we're going to do that for both. These numbers inside of here will be the same for both of them. So if one's 200, the other's 200. I have my negative radical 3 plus I again. I want to leave it in polar form. I want to find the complex cubed roots. So n equals 3, because I want cube roots. First, I need to get this over from Cartesian over into polar. And so I find my r, which is going to be a 2. And then I would find the angle. Well, I know if I'm at a negative radical 3, 1, I'm kind of like right here. I'm in the second quadrant, so I'll say, let's find cosine. X divided by r is my cosine. What angle has the cosine of a negative radical 3 when I'm in the second quadrant? 150. This is theta naught, right? That's that starter. This is the one that we're going to be taking the root of. So we're going to start with this and break this up. I'm taking the third root, and in goes my radius. Theta naught goes on the top here. Again, this is n. So all those 3's are n's. Instead of 2 pi, for whatever reason, when we take complex roots, we always use degrees, so we'll go back to 360. It actually makes life a little bit easier. So it'll be 360k over the n again for both of these. And now what you're going to do is the same thing that you did when you were solving trig equations. You're going to let these k's tick around 0 up to the 1 less than n. So we'll have 0, 1, 2. So we'll go to 2. All right, so we plug in a 0. Well, we didn't plug in anything yet. We did our division. And so this is for when k is 0. My 120s will be wiped out. And so my first root, when k is equal to 0, my starter, is kind of like when you solved and you got that first solution and then you started to add on to that. So my first root, when k is 0, is the cubic root of 2 times the quantity cos of 50 I sine 50. Tick around. 1. Well, 1 times 120 is 120. Both of those will get added on to the 50. So now I got the cubic root of 2 times the quantity cos 170 I 170. That's my second root. Third root, when k is 2. 3 radical 2, cos of 50 plus, well, whatever 120 times 2 is. Of course, we know that's a 240, and so I have 290, 290. And we can't do a 3 because 3 is going to be way too big, right? 3 times 120 is 360. That loops you out of the circle at a 410. You can't give out 410 degrees worth of pizza, right? You only have 360 degrees. And there's no picture. That's so sad. And so if I was going to draw a picture, which I probably would, it would look like this. My first root is at 50, and I'm going to say that's right about here. There's my 50 degrees. And this is when k is 0. My next one starts here, but goes another 50 degrees. And so I only want 3 slices. So I cut this slice first. I add on 120, and I wind up at the 170, so I'm going to be down here. This is when k is equal to 1. Oh, you can't see the 1. There we go. And then from here, I need another 120, and that takes me over to the 290. Let's see, right about here. And that, when I cut that slice, that k equals 2 slice, it finishes this piece in here. So I have one slice of pizza that's like you cut one side of the slice of pizza and not the other, like you went around in a circle. I guess it is a little strange, but the whole process is a little strange. Here's my second slice. And here's my third slice. 3 slices of pizza. They're all the same size. I began cutting my pizza at the 50-degree angles. That is how you find complex roots.